All right, today we're talking about something straight out of a movie. We're going to break down how NASA literally smashed a spacecraft into an asteroid on purpose just to see if they could move it. Yeah, it's pretty wild. Let's dive in. I mean, it's the big one, right? The question we've all seen in movies. Could we actually stop a giant asteroid from hitting Earth? It sounds like science fiction, but for scientists, this is a very, very real problem they're trying to solve. Like, if we saw one coming, what could we even do? So NASA figured, enough with the theories, let's actually try it. And back in 2022, they did just that. They ran a real-world, full-scale planetary defense test. And trust me, the results were, well, they were spectacular. So the mission was called DART, and that's an acronym, of course, for the Double Asteroid Redirection Test. The name pretty much says it all, right? This was literally the first time humanity has ever tried to purposefully move something out there in space. Okay, so here's how they set up this cosmic game of billiards. The target wasn't just some random rock, it was a small asteroid moonlet, a little guy named Dimorphos, and it was already orbiting a bigger asteroid, Didymos. The goal? Super simple, in theory. Just smash a spacecraft into it going 14,000 miles an hour and see if we could nudge its orbit. And here's the really important part. Neither of these asteroids were any threat to us. This made it the perfect, safe little laboratory out in space. All right, so after all that planning, after a 10-month journey through the solar system, the big moment finally came. The big question. Did it actually work? So how do you even measure success here? Well, the astronomers were watching one thing: how long it took Dimorphos to go around its big brother asteroid. Before the hit, that orbit took 11 hours and 55 minutes. Now, NASA said they'd call it a win if they could change that orbit time by just 73 seconds. That's it. A little over a minute. That was the goal. But the actual result? It didn't just meet the goal. It completely shattered it. The impact shortened the orbit by a full 32 minutes. 32, that's more than 25 times what they were hoping for. This wasn't just a success. It was an absolutely mind-blowing success. And yeah, the importance of this was not lost on anybody. NASA Administrator Bill Nelson said it best. He called it a watershed moment for planetary defense and all of humanity. And he's right. For the very first time, we proved we could actually change the path of something in the cosmos. Okay, but why was it so ridiculously successful? 25 times more effective than expected. Well, it turns out that the spacecraft simply crashing into it, that was only half the story. The real kicker, the big surprise, came from what happened after the collision. And the key to this whole thing is a word you're going to want to remember: ejecta. That's just the scientific term for all the stuff, we're talking tons of rock and dust, that got blasted off the asteroid's surface and flung out into space by the impact. You see, the deflection came from this brilliant 1-2 punch. First, you get the direct hit, the kinetic impact. That's the spacecraft giving its own momentum to the asteroid, kind of like a cue ball hitting the 8-ball. But here's the thing, that wasn't even the main event. The second and way more powerful push came from what's called ejecta recoil. Think about it. As all that debris shoots off in one direction, it acts like a rocket engine, creating a recoil that shoves the asteroid in the opposite direction. It was that recoil that gave it that massive extra push and made the whole thing so effective. And the best part is, we don't have to just imagine what this looked like. The Hubble Space Telescope had a front row seat, and it captured some absolutely jaw-dropping images of the whole thing. Okay, so check this out. Just a few hours after the impact, Hubble saw this. You can see this perfect cone of material just blasting away from the asteroid. That's the initial explosion, that high-speed ejecta shooting straight out from where DART hit. But then, fast forward a couple of days, and the whole picture has changed. You've got the gravity of the main asteroid and even the super gentle pressure from sunlight starting to work on that debris cloud. They start sculpting it, pulling the slower bits into these beautiful curved streams you see here. And then, over the next week or so, those streams just kept growing. Until, wow, you get this, a spectacular tail stretching over 1,500 kilometers long. DART basically gave this asteroid a temporary artificial tail. It turned it into a brand new active asteroid, making it look almost like a comet. Now, this comparison is really fascinating. On the left, you've got DART's ejecta. See how it's all clumpy and structured? On the right, that's from an older mission back in 2005 called Deep Impact, which hit a comet. Its cloud was way more, I don't know, poofy or diffuse. And scientists think this difference tells us something really important about what Dimorphos is made of. It's probably a rubble pile, basically a loose collection of boulders and rocks all held together by gravity, which is why the debris flew off in these more distinct streams. So, after all that, what's the bottom line? What did we actually learn from this absolutely unprecedented experiment when it comes to, defending Earth? Well, first and most important, DART proved that this whole kinetic impactor idea works. It is a totally viable strategy. We now know we can hit an asteroid and we can move it. We also learned that the recoil from all that ejected rock and dust is a huge factor, maybe even the biggest factor, which is something we have to account for in any future plans. This whole mission gives us our first real-world data for how to actually respond to a threat. DART is now the gold standard, the benchmark for studying any kind of asteroid impact from here on out. But let's be real. DART was a test. A brilliant one, for sure. It showed us we have the technology. But this was on a small, non-threatening asteroid that we knew everything about. So if a much bigger, unknown rock suddenly appeared on a collision course, and we only had a few years to get ready, that question still hangs in the air. Are we really ready?